Yeah. All right. Well, of course, you can interrupt me at any time, and when I'm going too fast or too slow, just tell me. What I have 30 slides in all, so you can actually count how far I am. The intro slide is a summary, but is already concentrated on the Rush model, whereas the chapter is not. But I thought, why not start from the Rush model to summarize, and it also gives you the main philosophical concept behind the book, the difference between descriptive measurement and explanatory measurement. So the idea is, where we started from, is that it is nothing more than just linear regression, and that in the Rush model you regress on things that don't explain anything, like the individual persons and the individual items. And so you don't have any explanation for why the persons differ or for why the items differ. And that's what the intro says, not much more than that. On the second slide, I thought to introduce the whole chapter, starting from a common kind of design, which I called here the basic design, with single observations, meaning that from a set of persons, we have a number of observations, and it is commonly so that we have only one observation from a person. That is not the case in a test, though, but unless you think of a sum score, that is just one single observation then. But here I'm not yet as far as looking at the different items. Here I have only one observation for each person, and that's the observation that is circled. So I have on level 2, I have the persons from 1 to capital P, and then under those persons there are observation occasions going from U, from 1 to U, and they can be different from person to person. That's less important here. And at one occasion you make an observation for each person, and it can be a different occasion depending on the person. To give you an example, this could be a sum score, and the sum score could come from the 24 items that are introduced in the book, and those 24 items, they refer to 2 times 3 situations. There are 3 situations that refer to self to blame, and 3 that refer to other to blame. So that's what the 2 times 3 is. And for each situation you have 3 possible behaviors. They're not mutually exclusive. You can curse, you can scold, or you can shout. I'm not going to shout sometimes. I'm not in the mood to shout. Sometimes when I present this, I act it out. But not this time. And then a difference is made between, then there is a difference between wanting to curse and actually cursing. Of course, this is all verbal self-report, so one is not really sure what it actually means to say that you want to curse and that you would actually curse, because the response is not the actual cursing, but reporting that you would actually curse. When you multiply that, you have 2 times 3 situations times 3 behaviors times 2 modes of behavior, and all in all that is 24. Then I have A second example that I used for didactic reasons, but of course I'll have to find out whether it works out. This example, it's not in the chapter. It is the time taken by a person P to come by car from home to a party. So imagine I'm inviting you all and in a place near Berkeley, and you come to my party by car, and the observation is how much time it takes you to get to my party. So that's a single observation from each of you, just like a single sum score from each of you. Now, when you would want to explain these data, that's the next slide, you could ask questions like, why has Peter a score of 40 whereas Linda has a score of only 20? And here are some provocative explanations like, because he's Peter and she is Linda. I think that's the kind of explanation we're giving in a regular IRT model. Which is not an explanation, of course, it's trivial. Or some other, like some people are more verbally aggressive and verbal aggression is normally distributed, and well, this is just one person sample from that distribution. I've written this up this way because it doesn't sound good, and it's getting even worse when it comes to time it takes to come to a party. Why does it take Eric 40 minutes whereas Jane did only 20 minutes? And when you then would respond, because he's Eric and she is Jane, that does not make sense at all, of course, because you would immediately think, well, it's going to depend on the distance from here, and it's going to depend on the car they have. And it's only then there would be an explanation. And the amazing thing is that when we measure people in educational measurement, we don't do that much. We attribute the score to the person and not so much to an explanatory factor. What I want to say is this is the kind of explanation we usually give when we do implicit explanation, when we do item response theory modeling, and it's nothing more than just description. Now suppose we buy this kind of explanation, which is actually only a description, then a reasonable model would be, and there appears the classical test theory equation, I think, perhaps with somewhat different symbols. You have an observation y pu. It is person P observed at occasion U, and that observation is consists of two elements. There is mu P, and mu P is the mean for person P over possible measurement or observation occasions. That's what we call the true score, I think. You call it a true score as well in Berkeley? Yeah. And then there is the error term, and we make a couple of assumptions about the error term: normal, distributed, independent of mu, and variance equal for all persons. This is on the next slide. Oh, I sometimes forget that you don't see the presentation, but I'm now on the next slide with just the formula where the two parts of YPU are identified. One as the random component, that's a random thing, and that's associated to what I've called level 1 on one of the previous slides. You might look back or not, you may remember, I don't know. So here we have a random thing, epsilon PU, and on the other hand we have a systematic part, and that systematic part has a subscript P, and that refers to level 2 and not to level 1. It's black, black, black. Where my slides are black. Like, are those the only black slides you have? Is the rest okay, or is everything black? Is it just black, or is only the background black? Wow. Is there, Andre, is there a way to show them the presentation instead of my head uh, for a change? It might not be bad. You see, you see the slide? The slide repeats the formula, and it identifies the epsilon as the random component, and I'm building up here because in 10 or 15 minutes or earlier we will have 3 components. Here is the first. I'm building up towards 3 components, and here is the first identified. This epsilon is the first building block. And the other element is the systematic part, and it's a number, it's a parameter that goes with a person. All right. You can read the next slide again, yes? It's number 7, and it's about true explanation. Now we come to true explanation. Well, we know that when it comes to verbal aggression, that males have more of it than females. And so one explanation could be the score of Peter is higher because he's male and she's female. Or because he is high on trait anger. Trait anger is a personality dimension, and some people have more of it than other people. It's not the most challenging explanation, of course. It's in a way also descriptive because it refers to a trait, but that's the kind of explanation you would find in personality psychology. And then when it comes to Eric and Jane coming to my party, well, it's evident that the one who lives farther away is going to need more time, and depending on the car, perhaps also the speed is going to be slower, and we would accept that easily as good explanations. They explain the observation in terms of properties of the person, and I'm now considering the distance from my home as your property, as a property you have, and the speed of your car also as your property. And that is, of course, better than just a name or referring to you as a draw from the population. Now, suppose we buy this kind of explanation, then we are not going to explain the error term with these factors. Now, what we explain is the mu of person P, and what you see here is a linear equation with 2 predictors, with 2 person properties, one for gender of person P, and one for trait anger, and an intercept. And the weights are these strange looking thetas. I will use 2 kinds of thetas just like in the book. This is the second type, and they're regression weights. the regression weights for the true score. And they explain the differences between the persons at level 2. Level 2 is the differences between persons in terms here of gender and trait anger. Now, as is the case, this is the case here, that gender and trait hanger are not so good as predictors, so as explanatory factors. So we won't be able to explain all individual differences in the sum score just by these two factors. Therefore, we would like to have an additional error term. Now, an error term at level 2, which is the part of the true score that cannot be explained, in this case, by gender and trait anger. So there is a problem there. If we don't have a perfect prediction of the true score, then we need again an error term, but now an error term that comes with level 2, whereas the previous error term came with level 1, with occasions of observation, with the observation occasions, whereas this error term has a subscript P and comes with a person. Now, in case also this error term is normally distributed, one cannot distinguish between the two. They merge. This actually means that the mu p we are working with is a conditional mean. It is the mean of y pu given the gender, the value of the gender and the trait anger. Is that clear or somewhat clear? Yes. Oh, that is my. Oh, that's good that you noticed, because that's my fault. That's my fault. I mean, it should be the same theta. That is, yeah. There might be more typos, and warn me when there are. Here is this zeta is meant as a theta, the same theta as in the first formula. The only change is that we have an additional epsilon added. Now, when you combine the two ideas, we have two new formulas. Well, one I have already shown, which is the mu plus epsilon, and then the other is the linear equation for mu. André, kunt jij... You see it? No? He's working on it. Yeah? Uh-huh. Well, here you also see that all what does not go in the linear equation in the sigma theta z goes in the epsilon. The idea of the previous slide that the two error terms merge. The error terms from the two levels. Now, when we start the index g at 0, then we also have the intercept in the sum. Huh? Then we have theta 0 times z p0 That's going to be the intercept, on the condition that we define the z as the zp0 as equal to 1 in all cases. For all persons, that means. All right. I think also for the next, you will have everything in black. So also here we need the slide from here projected in your class. You see it? Yeah. Well, we now have a second component. And the second component is the linear equation. And it's called the linear component. And, well, you know it. This is just naming it. So we now have names for the two parts. And these are two building blocks of the more general model I will present soon. There is not real new information in this slide, it's just naming. Next slide is again on the party. And this is to introduce a third component. And I'm using a trick, I'm actually misleading you, but I hope you're willing to take it. Why does it take Eric 40 minutes, whereas Jane did only 20 minutes? Well, we already have an explanation. It's because he lives farther away and he has a slower average speed. Now, when we would use a linear equation here, that does not make much sense because time is not a sum of distance and speed. Time equals distance divided by speed. So we have a multiplicative function and not an additive function. However, when you take the logarithm of time, then again we have a sum. It's a difference, but a difference is a sum. Subtraction is like addition. Well, we can now build again a linear function, but now for the logarithm of mu. So the logarithm of mu is a linear function of the logarithm of distance and the logarithm of speed. And we have again the linear equation of one of the previous slides. And you're into black again, is that correct? Yes? So I can explain when you have to confront the black. You see the slide now projected? It's the one on generalized linear model. And this is to introduce a third component, a third building block. And that one refers to the transformation that is done. The transformation is the logarithm. So when you read from top to bottom, we have first the classical theory formula with the random component. When you go down, we first transform the mu. We take the logarithm of mu, and that is then eta. And this transformation is done with the link function, or the inverse of the link function. And then we explain the logarithm of mu by a linear equation. And this is called the generalized linear model because there is a transformation in between. there is this link function. So we're using the linear model, but we allow for a transformation halfway, so that it is not the original mu, but a transformed mu that is a linear function of the properties of the predictors. And this now is the generalized linear model. Now, when you think of the example, and that's why it was misleading, you can rather easily transform it into a regular linear model by having an interaction term. This